I'm now going to talk about big O notation, which is going to give us a nice way to measure how much space a computer program uses and also how much time it takes to run. To begin with, let's consider an example where we're storing a probability table for a random variable x. Of course, this table has alphabet size of x entries, which here I'll call k. And so by storing these k probabilities, these k numbers, then we fully know this probability table. Of course, you can say that we don't need to store k numbers, we only need to store k minus 1 of them, because the one we don't store is just going to be 1 minus the sum of all the other numbers. And that would be true. So we can store k numbers or we can store k minus 1. Both are okay. The point is that the number of numbers that we're storing here is on the order of k. So linear in k. And so for big O notation, somehow we'll want to get at this idea that this minus 1 doesn't really matter. Somehow what matters is that it's linear in k. Alright, let's look at a different example where instead of looking at space, we're looking at time. Specifically, how much time does it take to compute the marginal distribution for x by summing out over all little y in the joint probability table. And so instead of measuring time in terms of, for example, seconds, what we're going to do is instead think about how many basic operations we need to run, where basic operations are things like addition, multiplication, table lookups, assignment, and so forth. The idea is that somehow these basic operations each take roughly the same amount of time, so we'll instead just count the number of basic operations. Let's look at this particular example, where to compute this marginal, we're going to have to iterate through each possible little x, and for each possible little x, we're going to have to iterate through each possible little y in order to compute this sum. So let's look at this in code here, where I'm representing this joint probability table in a dictionaries within a dictionary representation, and I'm representing the marginal px as a dictionary, which I initialized to be a empty dictionary at the beginning, which I'm going to fill in. And again, I'm going to iterate through each possible little x, and I'm going to compute out a sum. Okay, so this code here computes out this sum, and then once it figures out that sum, which is stored in total, it's going to store it into px of little x. So how many basic operations do we need to do? Well, let's say that this assignment here takes something like 1 basic operation. Of course, it might actually be something greater than 1 because we do some dictionary initialization, but let's say this is something like 1. And here we have this total equals 0, and let's say this assignment is also 1 basic operation, but we're not running this line only once, right? We're running it alphabet size x times. And so let's say for simplicity that k is again the alphabet size of x, and let's for simplicity say that this is also equal to the alphabet size for y. And so the number of times I need to run this line is going to be 1 times k, okay, the alphabet size for x. Then in this line here where I'm doing this total equals total plus the joint probability table evaluated at x and y, this requires a table lookup, which for simplicity, let's say that's 1 basic operation. In reality, in order to do this table lookup with dictionaries within a dictionary, you might have to do a number of different basic operations, but let's say for simplicity that this lookup just takes 1 basic operation, and then we have an addition of 2 numbers, so let's say that's another basic operation, and then an assignment, so let's say yet another, and then of course this thing gets run alphabet size of y times the alphabet size of x times, so that is times k. Okay, and lastly here this line we're taking total and assigning it to here we have to index into the dictionary with little x, and maybe that takes a basic operation in itself, so let's say there's that 1 plus this assignment, so let's say it's 2. And of course we have to repeat this alphabet size of x times, so times k. And if we sum up these values in red, we get 1 plus 3k plus 3k squared. Again, I was being a bit sloppy with the 1 here might actually be more than 1, but still some constant. And here, this lookup might be more than 1 as well, and so forth. But the point is, it doesn't matter if this is 3 or 5 or whatever. This whole thing is going to scale something like k squared. Okay, the dominating growth term is this k squared here. And so big O is going to let us say, yeah, this thing grows like k squared. Let's formalize what big O means. So we say that a function f, which you can think of as the amount of space a computer program uses or the amount of time it takes to run, f is going to depend on some parameter, let's say n. Earlier in both of the examples, the parameter was k. Okay? Here I'll just call it n. So we say that f of n is O of g of n. So O in big O stands for order. So f of n is order g of n if f of n is in some sense actually upper bounded by g of n. So let me illustrate what's going on here. So we have f here, which grows as a function of n. So I'm going to do an example where f ends up growing linear. So at the beginning, let's say f kind of does something a bit crazy, and then it finally tapers off and becomes linear. Okay? And so the basic idea is that after some n naught, it becomes well behaved. And you can think of it as, for example, here we had the -1, so when k is small, you start to feel the effects of this -1, but when k is large, you don't feel it. And similarly down here, when k is small, you start feeling the effects of this 1 plus 3k. Okay, so that's why at the beginning there's some perhaps weird behavior going on, but that's okay. After n is large enough, so when n is at least n naught, it's going to be nicely well behaved, where in this case it starts to look very linear. And then we have this function g, which, for example, it's this line here. And like we discussed earlier, somehow the constants don't really matter, so we're going to allow scaling g. So we scale g by some amount and go like, after n naught, g is always an upper bound on f. And so that actually is what we mean when we say that f of n is big O of g of n, is that f is in this sense upper bounded by g. So to turn what I just said into some mathematical symbols, we have f of n is O of g of n when there exists some n naught, and also there exists some constant c greater than 0, such that f of n is less than or equal to c times g of n. Okay, and this holds for all n bigger than or equal to n naught. So this here is just formalizing what I drew as a picture, and it is what the definition of f of n being O of g of n means. And notationally, when this happens, we actually write f of n equals O of g of n. So this equal sign is actually kind of weird, because you can think of it as this O of g of n somehow refers to a whole class of functions. They're upper bounded by g in the sense that we just talked about, whereas f is just one of those functions. Okay, so in fact, some people actually use the notation that if f of n is O of g of n, they write f of n is in O of g of n. Okay, but it is very conventional for people to just write f of n equals O of g of n. Okay, so going back to our examples, we can of course write that k minus 1 is O of k, and 1 plus 3k plus 3k squared is O of k squared. Okay, so that is big O notation in a nutshell.